In this video, we are going to go over an optimization under uncertainty for a very simple 3-bar truss. This is part 1 of 2. In this part, we want to prepare for a subsequent optimization under uncertainty that comes in part 2. Now, before you ever start an optimization under uncertainty or an OUU, you have to pick an efficient UQ method or a method for uncertainty quantification. When you look at the Dakota user's manual, you have a lot of different UQ methods that are available, but each of these have their different levels of computational cost. Some of these UQ methods might require you to run your black box function dozens, hundreds, or thousands of times. But since we are using FEA, that tends to take a long time sometimes just to perform one run, it's very important that we pick a very efficient UQ method. So what we're going to do in this exercise, we are going to look if we can use the so-called mean value first order second moment method. This is one of the cheapest UQ methods available. So if your OUU problem qualifies where you can use the MVFOSM method, take advantage of this method. So instead of running your black box function hundreds or thousands of times, you're running the black box function maybe dozens or hundreds of times during the OUU. Now, today's analysis model is the following. Again, it's a very simple 3-bar truss. Here's the diagram of this 3-bar truss. The top 3 nodes are pinned, while the 4th node is free. We are applying 2 different loads on this, so essentially we have 2 different load cases. I think a lot of tutorials only consider 1 load case, which is not good for us, because then when we want to do multiple subcases, we don't know how. But in this example, I want to show you what the process is when you have 2 different load cases. The uncertain variables are going to be the design variables. When you manufacture this 3-bar truss, every truss member that you construct or manufacture is not going to have the desired cross-sectional area. There's actually going to be some variation in that area. Now, given the uncertainty in the variables, we want to look at the responses. We want to look at quantities like the mean, the standard deviation. Specifically, what we want in this example, we want to run Nastran multiple times. We want to collect the mass, the stress, and the displacement for the truss members. And then we want to build this histogram of the responses. And if we want to use the MVFOSM method, this has to be satisfied. The distribution of the responses have to be normal or nearly normal. So here is an example of normal responses. These responses, R1 and R2, happen to be the responses from today's exercise. We go ahead and run Nastran a few times for different configurations or permutations of the variables. We collect the mass, stress, and displacement. Then we create these histogram or frequency diagrams. It's basically a count of how often we see the different response levels. Once we build these histograms, we assume a normal distribution and we plot that curve that you see here in orange. If the histogram fits within or resembles a normal distribution, that is evidence to us that the actual distribution is normal. And if it's normal, that's good for us because it means we could possibly use the MVFOSM method. Another second requirement is that you have gradients available for the responses. Since we're dealing with a solution 101 or linear statics analysis with simple mass, stress, and displacements, these responses are supported by MSC Nastran SOL 200, and SOL 200 happens to output gradients. So once we confirm in this exercise that the responses are normal, we know that we can get gradients for these responses. So the two requirements for the MVFOSM method are satisfied. So we can use that UQ approach for OUU in the future. Now on this slide are some examples of non-normal distributions. So here on the left is one example. We ran the black box function for all these different uncertain variables. We created the histogram, and then we tried to fit a normal distribution that is in this orange line. But you can see that the histogram does not align to the normal distribution. So this is evidence to us that the actual distribution is non-normal. So the MVFOSM method cannot be used for this example since, again, the distribution is not normal. Here on the right is another example. What we did is the same thing. We ran the black box function multiple times. We created the histogram. We tried to fit a normal distribution, and we honestly tried, but you can see here that the distribution is simply not normal. Unfortunately, it's extremely skewed to the right, if you can see from this diagram. So for these two examples, the distributions are not normal. You cannot use the MVFOSM method for this example. So here's a quick overview of some of the goals we want in today's exercise. On number one, what's the process to confirming the distributions are normal or not? After we run Nastran multiple times for the 3-bar truss, then we decide if we can use the MVFOSM method. Then we configure the bulk data files to output gradients. Then we discuss how to pick the optimal starting point for the optimization. This is actually very important for successful optimization. Depending on where you start the optimizer, it will either take a long time or a short time to converge to the optimal solution. And then another thing to consider, if you have thousands of constraints, that might cause the UQ to be very expensive. So it's important to reduce the number of constraints as much as possible. So I'll give you some guidance on how to reduce the number of constraints for OUU. And then again, we'll go ahead and configure the bulk data files for future OUU. Now, just in case you're new to UQ or OUU with MSC Nastran or Sandia Dakota, you're more than welcome to contact me here at this email address, and I'd be more than glad to get back to you as soon as possible. Now, let's go ahead and get started with this exercise. Now, all the steps I'm taking today are from this tutorial file. So if you're watching this video on YouTube, there is a PDF available at theengineeringlab.com. You can go there and access that PDF link. I'm essentially going to be following the same steps. So we are starting off at the home page of the SOL 200 web app. Let's go ahead and open the tutorial section and navigate to the UQ and OUU tutorial section. So here we navigated to the OUU section, and we essentially are looking at the first tutorial on the table. Let's click on this link called Starting BDF Files. This downloads a zip file to our desktop. Let's open that zip file and let's go to directory A. And if you look at this bulk data file, it's already finished. The assumption here is that you've already configured this in a separate tool. You've configured this for SOL 101 or linear statics analysis. You have two load cases, you have your nodes, your elements. This is a run ready bulk data file, and this is the starting point for today's exercise. Now, this is what we're going to do. We are going to go and open the machine learning web app. And let's go ahead and take a step back and do this. We want to consider responses, mass, displacement, and stress. So we need a result file to pick results from. So here what I've done is I ran Nastran, and now I have the F06 and the H5 file. The H5 file contains the stresses, the mass, and the displacements. I'll be cherry picking the results from this file in a moment. Now, what we do here in the machine learning web app, we first select the bulk data file that contains the 3-bar truss. Then we pick the uncertain parameters. that are going to be the cross-section area for the PROD entries. Then we go to the responses section and we upload the H5 file. Now, one thing about this section, you can resize the different sections with these arrow buttons at the top right hand corner. So I know there's a lot of action happening here, so just be aware you can resize these sections. Now here on the left, we pick the grid weight data set and we select the mass. Then we jump to the stress data set and we select the axial stresses. You notice anytime we select the response, here on the right is the corresponding response. These are the responses on the right that we are going to record during the sampling that we perform in a moment. Now let's go ahead and do this for the displacement data set. We'll select these displacements that are the displacements for node 4 for subcase 1 and 2. And so here on the right are all the responses that I'm considering. We want to perform what's called sampling. Sampling is a type of UQ or uncertainty quantification. So to do this, we jump over to Dakota, and now we click on Dakota here in the top navigation bar, and we select sampling here. So sampling, some of you might be familiar with the Monte Carlo method. That's a type of sampling. Today we'll be using a different type of sampling method called the Latin hypercube sampling approach. So we've selected sampling here as the U cube, but now we have to supply some information for the uncertain variables. Here we simply supply the standard deviation as 0.04. Some of you might be asking, okay, where in general do I get the standard deviations from? This would come from testing. You would actually manufacture, in this case, the 3-bar truss. You would physically manufacture it an n number of times. You find that the variation is not exactly 1 or 2, or the cross-section is not exactly 1 or 2. There's some variation of that. From all the different variation, you find the mean and the standard deviation for your variables, and that's how you get these values for the mean and standard deviation. So it's from physically manufacturing your structural or mechanical system. So let me look here at my notes. Now the notes I'm looking at are the steps from the PowerPoint or the PDF. So again, if you want to follow along, it's the PDF that would be the document to follow. Okay, now let's go ahead and jump over to the method section. So this method section is going to give you access to a lot of keywords from Dakota. Here you can click on display selected keywords, and this will reduce the number of available keywords. If you go to samples right now, it's configured to run 100 samples. So if this was the Monte Carlo method, it would run Nastran 100 times using a Monte Carlo approach. But you can see that our sample is LHS or Land Hypercube sampling. For the number of samples, we're just going to go ahead and pick 50. We ran a conversion study prior to this exercise, so we know 50 is a good enough number. Now let's go to downloads and download a new set of bulk data files. Now, like I said a moment ago, we are using Sandia Dakota. Sandia Dakota is a very useful tool for uncertainty quantification and optimization under uncertainty. Fortunately, the tool is free, the source code is free, and they provide pre-compiled executables that are also free. So it's a very nice tool to have if you want to perform uncertainty quantification or OUU. Now let's go ahead and start this sampling approach. And while this is happening, let me talk about the histograms for a quick moment. Now, here I can hear MSC Nastran doing its beep sound in the back. Let me mute my audio. So when you build the histograms, actually before that, sometimes you won't have histograms after your UQ. There is an alternative method you can rely on to tell if you have a normal or non-normal distribution. You can use what's called the skewness value. Generally, if you have a skewness value between negative 0.5 or positive 0.5, then you have a normal or nearly normal distribution. So anything between negative 0.5 and positive 0.5, this is nearly normal. If it was perfectly normal, I believe the skewness should be 0. So if it's 0, it's normal. Here you'll notice that the skewness values are actually within the range of negative 0.15 and positive 0.15. If you look at the first skewness value for response R1, that's 0.05. If you look at the next skewness value, it's 0.15, and then the next skewness value is actually negative, and negative 0.094. So these values that we saw a moment ago, these are all within the range of negative 0.5 and positive 0.5. So these are indication that we have nearly normal distributions. Now, here, if you look at the skewness values, they're a lot different. If you look here at the left, the skewness value is 1. So this is well outside of the range of negative 0.5 and positive 0.5. So since it's outside of this range, we know this is a non-normal distribution. So non-normal. And the same can be said for the second histogram here on the right. If you look at the skewness value, it's negative 7, which again is outside of that range of negative 0.5 and positive 0.5. Now, the sign actually gives you another clue as to what the distribution looks like. You can see that if it's positive, you can see the histogram is kind of leaning towards the left. If the skewness is negative, the distribution will be leaning towards the right. So the skewness value can give you a lot of information as to what the distribution looks like. So if you don't have time to look at the histograms, if you don't have time to build the histograms, you can rely on the skewness to determine if the response is normal, nearly normal, or simply not normal. Now let's go ahead and see where we're at with the sampling. Okay, so we have a status page telling us that it's running all 50 samples. One thing we can do is open the so-called Dakota output file. So this output file is going to give you information on what Dakota is doing. You can see here that Dakota has requested 50 samples, and now it's running Nastran for each sample. So here for the first sample are the values for the cross-section area. Here the blocking fork is indication that it's running Nastran. After that, it collects the responses for the mass, the stresses, and the displacement. And then it repeats it for sample 2, sample 3, and so on and so on. Right now, we are at sample 44. You'll notice that we have the variables and the statement blocking fork saying that it's running Nastran, but we don't have the responses yet. If we go back to this file, let's go ahead and open that file. After the sampling is done, it relocates the output file to workspace D. And here, if we go all the way to the bottom, we see the results of the uncertainty quantification. So let's go ahead and scroll up a little. You can see we are at sample 48, 49, and then at 50. Once we're done with the last Nastran run, the last sample, we've collected all the responses. We get summaries of the statistics. We get a table of the responses with the mean in one column, the standard deviation, the skewness, and the kurtosis. Now, you can look at this table and make your conclusions if the responses are normal or not normal by looking at the skewness values. Now, what the web app does, it takes the same results and it automatically builds the histograms for you. And if you go to the, I believe, table section, the same results that you saw in these tables in the Dakota output file are also available here in this table. So here we have the mean, the standard deviation, skewness, and the kurtosis for responses R1 through R11. But what we are interested in are the histograms. Now, we only have enough information to create the histograms, like you see here. What the web app does, it takes the mean and the standard deviation and it plugs them into the normal distribution function. So let's go ahead and find that equation online rather. So this is the equation, the probability density function for a normal distribution. So what we went ahead and did is, okay, let's take the mean and the standard deviation and let's plug it into this equation. And then we plot it here. So this would be the orange curve. If the histogram aligns to this PDF, the normal distribution in orange, perfect. That means we most likely have a normal distribution. And we repeat the process for each response. We build the PDF plot automatically and we look at the histograms. Everything looks good. Every distribution here, all the mass, stress, and displacement distributions seem to have a normal distribution. So then, now that we know that, let's go back to one of the questions that we had. Can the MVFOSM method be used? And remember that there are two requirements in order to use the MVFOSM method. And as a reminder, the reason we want to use the MVFOSM method is because it's one of the most efficient UQ methods available. Instead of running Nastran thousands of times, maybe we only need to run Nastran a few dozen or a few hundred times to perform the uncertainty quantification. So here are the two requirements for the MVFOSM method. Number one, are the responses normal? And the answer was yes, the responses are nearly normal as we saw from the histograms. Number two, do we have gradients available for the responses? We are using SOL 101 or linear statics analysis for mass, stresses, and displacement responses. Nastran SOL 200 can output the gradients, fortunately. So since the MVFOSM method requires gradients, we can provide gradients for the responses. So since the two requirements are satisfied, yes, we can use the MVFOSM method for the uncertainty quantification and the optimization under uncertainty in part 2 of this exercise. Okay, now there are a lot of other slides that give you a lot more information about what the MVFOSM method is, when is it reliable, when is it not reliable. I'm not going to go through a lot of those slides because they will simply make this short tutorial a 3-hour exercise. And I know a lot of people don't want to sit around watching a 3-hour tutorial. They want to get the information as soon as possible. So what I'm going to do, I'm going to glance over these slides and move on to part B. In part B, we want to do two things. Let me see if I have oh, okay. So I do have a slide for that. We want to do the following. We want to determine the best location to start the optimizer. So there could be a bad place to start the optimizer and there could be a good place to start the optimizer. So here on the right, I have a diagram to explain what a good place might be. So here in the solid blue line would be the response function as an example. Here, this response function happens to have only one variable, x1, and the response is r1. Let's suppose that we start the optimizer here in this orange dot. We'll call that the initial design. Let's suppose that the optimization assumes that the inputs are certain. Let's assume that the responses are deterministic. So there's no randomness. We know that the variables will always be the variables. There's no uncertainty, essentially. We use Nastran Sol 200 to perform the optimization, and we get this result at the bottom right. So I'll draw an X over this dot. We'll call this a Sol 200 solution. Now, this Sol 200 solution will have or rather, when you look at this diagram, we know that the OUU solution is not going to be equal to the Sol 200 solution. If you look at the Sol 200 solution and you calculate your worst case probability of failure, maybe you get a 50% probability of failure. That's not good for us. Maybe at the initial design, we get maybe a 1%, or no, maybe we get a 0% probability of failure. Maybe our aim is to get a 1% probability of failure. So here, this is one observation we've made in the past. We see that the OUU solution is actually close to the Sol 200 solution. So it would be in this region where the optimal OUU solution is. This is where you would find a solution that has a probability of failure of maybe 1%. But notice one thing, if we start the OUU at different points. Suppose we start the OUU here. The optimizer has to travel this distance. We'll call it distance D1. Now, suppose we start the OUU from the Sol 200 solution here on the right. Notice the distance the optimizer has to travel to the OUU location of the optimal solution. We'll call this distance D2. You can find that distance D2 is actually a lot shorter than distance D1. So basically, if we start with the Sol 200 solution, the optimizer has to travel a fewer distance than if we started at the initial design. That's good for us because I think I have this somewhere here. Let's see if we can find it. I may or may, oh no, that's in the next tutorial. But here, I think I remember the values actually. Oh no, these are going to be different values. So here, just to quickly sum up what I said. We want to select a good starting location for the OUU. What we are going to do is perform a Sol 200 optimization, and that solution is going to be the starting point for the OUU. This is because the optimizer during the OUU will have to travel a smaller distance to reach the OUU solution that is in this location. So maybe instead of having to travel this distance here, this would maybe require 100 Nastran runs. For this other solution, this different starting location, maybe we only have to run the Nastran solver 20 times. So I'll walk you through how to do this in a moment. Now, let's look at our starting point. So what you would do is the following. You would take the original bulk data file that's here on the left. So here it's configured for Sol 101, your two load cases, the mesh, the material, and the property. And you would configure this set of bulk data files for Sol 200 that's here on the right. So here you can see that it's now Sol 200. We have the desobj command for the objective. We also have definitions for the design variables, so the two cross-section areas. We have the mass, the displacement, and the stresses. So we've already configured the optimization prior to this exercise. Now, I'm going to skip over how to configure this optimization because there are already dozens of tutorials on how to configure a Sol 200. So I'm going to skip that part of the tutorial. I'm going to assume you already know how to get these files on the right. So this is going to be the starting point for part B. So here, let me quickly look at my notes and see where we're at. So here, let's assume you already have those bulk data files. So you would run Nastran to perform your optimization, and you would get the F06 file that contains the result of that SOL 200 optimization. So if we look here at the very end, we should have information about the SOL 200 solution. So here you could look, we've minimized the mass, the finite design is feasible, and then here in this 7th design cycle, we get the SOL 200 solution. We get the cross-section areas. So these two values are going to be the starting point for the OUU. So here in the initial column is the original values of the cross-section areas. So if you go back to this diagram, the initial values of 1 and 2 are here. And then the SOL 200 solution, this would be, I think it's 0.83 and 0.3. I forget exactly what the values are, but just know that's the difference here. We perform a SOL 200 solution to get this solution. This is going to be the starting point for the OUU. Okay, let me look here. Okay, now let's talk about screening constraints. Again, we don't want to consider every constraint because in some cases that just adds more computational costs during the OUU. So the F06 file contains information about every critical constraint, constraints that the optimizer is actually looking at. So what we are going to do, we are going to open the responses web app and we are going to select the F06 file. Now, and did I do this for the right? Here, let me look here. I think I've selected the wrong F06 file, so let's go ahead and redo this. Okay, so here we have a table of all the constraints that the optimizer was looking at. Here, if you look at the response type column, you'll see that the displacement response, the displacement constraint is not listed here. What happens is the following. If you have stress and displacement, buckling constraints, constraints on ply stresses, only the most critical constraints are considered because all the other constraints are most likely never violated. They're never approached. Essentially, the optimizer knows that you'll never violate those other constraints, so it's not worth considering the other constraints. Like here, we see that the displacement constraints are nowhere near being critical, so the optimizer doesn't even care about the displacement constraints. So here, right off the bat, we know we can ignore the displacement constraints. Ignore the displacement constraints. Now, what about stress? So what we do is the following. We look at the violated constraints. If there are any responses listed here, in this case there are 0 responses, any violated constraints would be critical. So those are the constraints you want to consider during the OUU. Now let's go ahead and look at the active constraints. The violated and the active constraints would be the critical constraints you would consider during the OUU. We look at the active constraints and we see that we have to consider some of the stress constraints. If you click on the show more information column, you find another trend. You find that element 2 is not listed here. So element 2, we can also ignore the axial stress for element 2 since it's not listed in this table. Now for element 1, you'll notice a pattern. It's only being, or rather the critical response for element 2 happens for only subcase 1. You'll find out for element 1, it's nowhere here. If we type in 1 to filter the table, you can see that for subcase 1, it's only element 1. So here what we do is we ignore the axial stress for element 1 for subcase 2, and we only consider the axial stress for element 1 subcase 1. Again, because if you look at element 1, the response from subcase 2 is not listed in the table, so we could ignore subcase 2 for element 1 and just consider subcase 1 for element 1. Now, I know this is a little bit complex, but the reason I want to go through this exercise is because you really, I would like you to have a good idea of how to screen the constraints. And here, if we look at element 3, which would be this row, we see that it's only critical for subcase 2. So here we'll say that we'll consider the axial stress for element, 3 for subcase 2. And we ignore the axial stress for element 3 for subcase 1. So here are the two critical constraints that we are going to consider for this exercise: the axial stress for 1 and 3 for subcase 1 and 2. And we're going to ignore the other constraints. Again, if the constraint is not listed in this table, it's most likely never going to be violated during the optimization, so we can ignore those constraints. In this case, the displacement constraint is never listed in this table, so we can ignore the displacement constraints. Then we looked at the stresses. We notice element 2 is not critical, so we remove element 2, and the only elements we consider for this OUUs are elements 1 and 3 for subcase 1 and 2. Okay, let me look at my notes just to see where the next part of this tutorial goes. Okay, so we've gone through screening, and now we discuss preparation of the bulk data files. Okay then, so here we went to the home page and opened the optimization web app. Let's go ahead and take those bulk data files. I have the SOL 200 configuration, and let's do a few things. Number one, let's remove the bounds on the variables. What is going to happen later on is Sandia Dakota is going to be controlling some values in the bulk data files. And we don't want to cause a conflict between Sandia Dakota and the bounds, so that's why we remove the bounds. And then I believe we go to settings after this. Let's see, let me look at my notes for a quick moment. So we remove the bounds, so then we go to settings and turn on the sensitivity analysis. And then I believe we go to the exporter and download our new set of bulk data files. Okay, so let's go ahead and extract the contents. So the second modification you want to make is in the design model.bdf file. So by default, the sensitivity analysis that we configured is going to output at most gradients for 10 responses for the mass, the volume, and the eigenvalue, and so on and so on. For larger problems, you are going to want more sensitivities or gradients for more responses, so we can increase this number here. So here we're going to vertically select and modify this value to output gradients for at most 100 responses for each response type. So suppose we had responses for mass and volume, we would at most get 200 responses, or we would get gradients for at most 200 responses for the weight and the volume. Now, one thing we want to be sure of, we want to make sure that we can run this bulk data file. So let's do a quick test run. Let's make sure we get an H5 file. Let's make sure there are no user fatal messages, or let's just look for fatal. Let's make sure there are no user fatal messages or system fatal messages, and here there are none. There is a fatal word, but something we can ignore. This is not a user fatal message, by the way. It's just some information. Here, if we look in this file, I believe we get gradient tables here. So here are the sensitivities. Again, if we want to use that MVFOSM method, we need access to the gradients, and that's what we have now. Let me look here at the tutorial and see if there's anything else that we need. Nope, I think that's pretty much it. Nope, I think that's pretty much it. Let's do a quick recap of this exercise. So this is part one of a two-part tutorial. And this part is basically preparation for the future OUU. We wanted to select the cheapest UQ method available, and one of those methods happens to be the MVFOSM method. We went through this qualification part A. We ran Nastran 50 times. We collected the responses. We created the histograms. We found out that the distributions are normal, so we can use the MVFOSM method. Let me take a step back. There are two requirements to use the MVFOSM method. Number one, are the responses normal? And number two, do you have gradients available? Number one, the responses are normal. Number two, the gradients are available. In part B, we actually went through this process of trying to find the best place to start the OUU, and we screened the constraints. We went through the process of doing both of those. And then in part C, we need access to the gradients. So we quickly configure the bulk data files to output the gradients from MSC Nastran. And that's it. You're done preparing your set of bulk data files for the OUU that comes in part 2. So I'll stop the video and then jump to part 2 of the video next.